פשוט הקרוב. כי אז אין ברירה, זה פשוט. מאחורה אתה יכול להיות כזה רגע, אולי אני אהיה בפייסבוק שנייה. בוא נראה מה חדש. אפשר להוריד מה? כן.
Hello. Good afternoon. So, just to remind you and me what we are doing, in the last 3 lectures, we devoted our time to what is called local analysis. We have a differential equation of certain type, let's say the area equation, and we want to study its behavior close to a point that we call x naught, that may be 0 or infinity or whatever you like. And we discovered that we can write the solution either as a sum of an infinite series of the form x to the n, or maybe we have here some coefficients that were x to the minus 1/4 times e to the minus 2/3 x to the 3/2 times the sum of a n x to the minus 3/2 n or something like that, so on and so forth. Right? One of them was around an ordinary point and around a singular, irregular singular point. We get something like that. And the important thing was that this series was a convergent series. It was a Taylor series. While this series was an asymptotic series that do not they do not converge, they diverge. And we have learned, and the question was what to do with such a series. So we have suggested one possibility, which is optimal truncation. So we said, okay, if the terms of the series are going like that, because it's an asymptotic series, we can stop the summation just before the smallest term in the series, and this implies that our accuracy is as close as the size of this term, which in some cases will help a lot. In other cases, you know, if the series is going like that, then it gives us no benefit. Okay, this was, as I said, now. The natural thing to do now in this lecture and the next one is to extend, and this is what I told you last time that I'm going to do, is to extend this analysis, and now instead of local analysis around x naught, maybe we want to put an epsilon here, like something like plus epsilon times y, and to analyze this function as a time series in epsilon, not in x around the distance from some x naught, right? Not something like that, but something like sum over n of a of say fn of x epsilon to the power of n, something like that. Okay? This is perturbation theory. We will do that, of course. But instead of doing it now, I have decided to pause a little bit for a few reasons, and to speak not about, but again, you also understand that in perturbation theory we are going to end up with the same kind of diseases. So instead of delving into the realm of perturbations and global analysis, right? I would like to devote some time to the to speak about summation of series. Right? We have a problem. We discovered that we have a problem. We have sometimes we have series that converge, but they may converge very slowly. We may need like 10 terms or 100 terms in order to get a reasonable distance from x naught. And there are the series that diverge. So I would like to devote this lecture to the question of summation of series. Now, this sum sounds extremely technical, right? However, as you shall see, there is a hidden title to this lecture, and the next one, I guess, which is generalization. And generalization is extremely important conceptual issue, in particular in the era of AI, right? So have in mind that although we are speaking about some things that we look to like completely technical, I will try to give some notes that will open your eyes, I hope, to the generic or the general implementations of the ideas behind this technique. So strictly speaking, the lecture will be devoted, this and the next one I guess, will be devoted into 3 parts. The first one is how to sum convergent series. Second, how to sum divergent series. Third, how to sum divergent series that you don't know the elements. Right? So this is plan. Good. So to begin with, let's take, I will try to present quite shortly 2 methods aimed at summing convergent series. Okay, and let's take a concrete example. You know what is 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 and so on. What is that?
Minus 1 over 12.
Hmm?
Minus 1 over 12.
No. No.
Minus 1 over 12 is 1 plus 2 plus 3 plus 4.
What is that?
Is it a function?
No.
It diverges.
It diverges? No. If you have pluses here, the absolute value of all the terms is the harmonic series. And the harmonic series, as I say, diverges, which implies that this series, although it converges, it do not absolutely converge. Right?
Right.
Okay? Have this in mind, that this series do not converge absolutely. But what is this series?
Negative 1 over 12.
No, somebody already suggested that. But no, this is a convergent, this series is not absolutely convergent, but it's a convergent series.
To 0?
To 0? No. Okay. This is by definition LAN 2. And by the way, a few years ago I was teaching high school students, first year electromagnetics. I don't know why I wrote this, and while I'm writing, somebody from the audience said LAN 2. So give respect to the Tichonist. So, okay, and what is the numerical value of LAN 2? Just to have it on our, so it's 0.6931. Now suppose, okay, now the way one usually sum series is what? Starting, I mean, the numbers are getting smaller and smaller, so apparently if we will calculate the sum of the first n terms that we defined last time, and we will take n large enough, we hope to be close enough to this number, right? So let me just tell you what, okay, so can you help me now? What will be S1?
1.
1. What will be S2?
F.
Half. What will be S3?
F6. Power 6.
S3 is 0.83. S4 is 0.583.
0.7.
S5 is 0.7 what?
83.
83. This is S5, sorry. S6 is what?
0.06.
0.6166. S7
0.775.
0.759. And S8
0.6.
0.6345. Okay? Now, you can convince yourself that, so you see, I calculated the 8 terms, the first 8 terms in the series, and instead of 0.69, I've obtained 0.63, which is the still deviation of about 7%, something like that, right? So it's not, the convergence is not fast. And the reason is that these numbers are not going down fast enough, right? So usually after the nth, after the nth partial sum, I will have a mistake that is proportional to 1 over n. Okay? Typically, right? Not exactly, but this is order of magnitude. So this is a slowly converging series. Okay? And I would like to draw your attention to another thing, which is that if I will plot Sn as a function of n, where this is the actual number that I would like to call L. So L is a solution, 0.69. Okay? So I am starting at what? I'm starting at 1, which is here. Then I'm, when n equals 1, I have 0.5. Right? The proportions are not good. 1 is here, say this is 0.5. Right? Okay? In 2, what I have? 0.83, 3, 0.58, 4, 0.7, something like that. So you see what's happened, right? It goes up, down, it misses, each time it misses by something, and it goes zigzag to the right answer. So the general trend, you know, is tack, 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 and it converges eventually to the right answer.
So
Yes.
it could be described as an underdamped oscillation, no?
Maybe. Okay. So here is the first brilliant idea of Mr. Shanks.
You can take them as couples.
What?
You can take them as couples.
No. The idea of Mr. Shanks is as follows. He said, let's model the series. Right? I would like to model the series in the following manner. I would like to say that Sn is, at least when n is large enough or whatever, the right answer plus a times b to the power of n, where b is negative. Why b should be negative? Because of the zigzag, right? Because I want to have how do I say that? Yes, okay, whatever. Because of this zigzag pattern. I should have positive, the negative, positive, negative, tack, tack, tack. Okay? Are you with me?
Shouldn't it be negative n? B to the negative n?
Sorry?
Shouldn't it be b to the negative n?
I didn't.
Shouldn't it be b to the negative n?
No, it's b is negative. B is negative. It's minus 1 times to the power of n times absolute
but then
value.
it blows up at large n.
No,
No,
can be smaller than 1.
Oh, so it's
B
greater
is
than negative 1.
B is negative. B smaller than 1 and B is negative. And therefore it gets smaller and smaller and smaller. So you have overshoot, undershoot, overshoot, undershoot until you arrive at the right answer. Okay? Now, okay, so, and here comes the black magic. No, this is not, this is the white magic. Okay? So Sn minus 1 by the same token is L plus A b to the n minus 1, and Sn plus 1 is L plus A times b to the power of n plus 1. If Shank's model is correct, this is how it looks like. Now Shanks looks at these three equations and said, hey, if this is true, then I can calculate L immediately. Why? Because I will say that Sn minus 1 minus L, sorry, no, I want Sn minus L divided by Sn minus 1 minus L. This is what?
B.
Sn minus L is A times B to the power of n.
B.
And then I should divide it by A to the B to the power of n minus 1, right? So what I obtained is B. And please agree with me that this is also equal to Sn plus 1 minus L divided by Sn minus L. Okay, so I don't have to know A and B. The whole thing is that I have no idea what A and B are, right? But I know because and I don't know what L is. So my goal is to calculate L without getting into the calculation of A and B. And now I have a way to do this because now it says that Sn minus L squared, which is Sn squared minus 2SNL plus L squared is equal to Sn minus 1 Sn plus 1 minus 2 minus L, sorry, Sn minus 1 plus Sn plus 1 plus L squared. You see, I multiply this by that and is equal to this times that. Okay? And fantastically, the L squared goes away. So I have a formula, and my formula is, how do I write it? Okay, let's write it well. Here. L, that's my goal, will be Sn squared minus Sn plus 1 times Sn minus 1 divided by divided by 2Sn minus Sn minus 1 minus Sn plus 1.
Where does the O squared cancel out? Where does the O square...
Because when I multiply this by that, I have plus L squared. And when I multiply this by that, I have plus L squared. So it cancels out. This equals to that.
Okay.
Both of them have L squared. Okay? So this is a formula that Shanks derived for us, right? And it may serve as an accelerator of series convergence, right? You see, I've calculated the first 8 terms, and I ended up with 0.63 instead of 0.69. Okay, so still a substantial deviation. What happened if I'm doing Shanks? So I've seen there is somebody who is making here fast calculations. So please, let's ask what is L, which is now S2 squared minus S1 S3 divided by 2S2 minus S1 minus S3. You see? The first place, I need 3 partial sums. 3 consecutive partial sums. So let's take these 3. Can you tell me what the answer is? S2 squared is 1/4.
0.698.
No. Well. Yes. You did this calculation. You have a calculator. Oh, okay. So if I'm using these 3 for Shanks, I will get 0.6984. Quite close. You see? With only first 3 terms. Okay? Now, what will I get from these 3? Okay, I can tell you that in my notes, I have 0.69444. Okay, and from these 3, I can obtain 0.692424. Extremely close. Okay. Now, of course, I can go down here, but I can be even more sophisticated.
To average those numbers.
I can Shanks the Shanks, right? So now I can take these 3 and Shanks them, right? So I will call this let's say S10, and this is S, right? This is a series S1, and I can put them here. And if I'm doing it for these 3, I will get, I think, 0.693277. Yeah, so I got 1 part of 10,000, right? By using only the first 5. So the first 5 by themselves took me to 0.1, order 0.1, right? So here the mismatch was around 0.1, and here, right, I can use them and get something with where the mismatch is 10 to the minus 4. Okay, you understand what? So this is the trick of Shanks.
You can do it only but if it converges.
Of course. Now, okay, now what does that mean? what are the conditions for this to work?
You need to have
Alternating series, but there is something else. I have some expectation. The expectation is a basic assumption of Shanks. That it goes like that and goes down, down, down. Because I can take the same series, and now in the 100 term, I will say, well, all the ANs are the same as are minus 1 to the power of n over n, which is this series, right? Except A100, which is 10 to the 10 to the 10 to the 6. Right? And clearly I will make Shanks for the first 5 terms or the first 99 terms, and I will not be able to catch this. Right? So it's not only that, but we want the series to behave nicely. You see? Not to be evil series that you know, have something that goes down, 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 and then bang, this is Shanks. Okay? For the moment, this is just a good advice of how to sum up series fast. And people told me, no, you don't have to teach it, because nowadays the computers are fast enough that there is no problem in summing up the first 1,000 or million terms of the series. You don't really need to Shanks them. But I want to give you the general outlook for the future. Okay. So, as you pointed out, a critical feature of the series for which we apply Shanks is that we have alternating overshoot and undershoot all the time. Now, what's happened when you have a series that do not have this property? Okay? So, suppose you have a series that do not have the Shanks property and is converging but not with overshoot and undershoot. If you want an example, so my example will be the following series: 1 plus 1 plus 1 over 4 plus 1, 1. 1 plus 1 over 4 plus 1 over 9 plus 1 over 16. Tack, 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 tack. What is that?
Pi squared over 6.
Pi squared over 6. Right, this is the sum of 1 over n squared from n equals 1 to infinity, or if you want it is zeta function of 2. Riemann zeta function of 2. Okay? And clearly, if we now calculate what are the partial sums, so S1 is 1, S2 is 5/4, S3 is
1.366. 1.366.
1.366. What is pi squared over 6, by the way? What? It's weird, I didn't wrote it.
1.644.
1.644. Right? So what is S4? Something like that. So you see that what's happened here, this series have a different behavior. If this is Sn, this is N, and this is L, right? Then this series just converges from one side, so it goes like that. It do not have the Shanks property. Good. So what one does in such a case? This answer was discovered by I guess, the most brilliant physicist you never heard of, which is Richardson. Have you heard about him? So, among other things, Richardson invented the weather. I mean, the weather was before Richardson, but Richardson realized that you can predict you can give a weather forecast by solving 6 coupled differential equations that make a contact between the temperature, the water vapor, the wind velocity, and blah blah blah. And you can answer what will be the, if you can just solve these equations, you can answer what will be the weather. I mean, you measure the situation now, and you can predict the weather for a few days in the future. Right? This was a discovery of Richardson. So Richardson decided to do a weather forecast, to solve, to get initial conditions, to solve the equations, and predict the weather. Fortunately enough, they had a day in the Netherlands where they raised balloons and they measured all the barometric pressure and all the important quantities that were required by the theory. And Richardson took the initial conditions, plugged into his equations, as I said, 6 coupled differential equations, and decided that he wanted to integrate this equation in time to the future. Okay? Now, this was a very difficult task, right? Richardson, so at the more or less the same time, World War I escalated, and Richardson have recruited to the army. He was not actually recruited to the army because he was quicker, like Eddington, and they refused to. I mean, they are pacifists. Okay, so instead of having to fight, he was an ambulance driver. And at nights or whatever, you have some free time. So he was staying in France, in some living on a stack of hay, ערימת שחת, in some Assam barn of some French peasant, and there with a pencil and a piece of paper, he simply integrated the equations. What I tried to teach you in the course of numerical analysis, but without computers. Just delta t is 0.01, and then x of t plus delta t is x of t plus delta t times, and so on and so forth. And because he was involved in such horrible calculations, he invented quite a few methods to cut corners, like this one, the Richardson extrapolation. And just to end up the story, so after like half a year of calculations, he was able to predict the weather, but it was not a prediction at the time, for half a day after the measurement, and it failed miserably. So after the war ended, he published a book in which predicting weather, providing weather forecast by calculations or something like that. Nobody purchased the book. I mean, it was one of the worst sellers of all times. But what is really interesting is that Richardson envisioned a way to mechanize the process. So he understood, okay, I spent like half a year in a barn in France to calculate things with paper and pencil. He wanted to deliver the mission to computers, right? But he didn't know what a computer is. When he was speaking about computers, he meant people that will compute, okay? So what he envisioned is kind of, a stadium, like a basketball stadium, with all people sitting down and doing calculation, and in the middle there is a CPU, which is a group of people that are delivering tasks to the, and this will be the computer. This was what he suggested. Now, and as I say, nobody took his story. I mean, nobody cares, and he moved on. He did, all the important, not all, but like half of the important results in the field of turbulence and things is Richardson. Now, after World War II, they do have computers, okay? And the main drive to develop the computers was the planning of the nuclear arms, that you want to calculate what's happened when neutrons are going through such and such, how many neutrons are going to leave the uranium sphere before triggering the fission of other uranium atoms, nuclei, and so on and so forth. So this was, but one of the people that was involved in all that was John von Neumann, and von Neumann wanted the American government, the federal government, to spend money on computers even after the war ended. So he wanted an excuse to explain them why. So his idea was to, now that we have computers, we can implement the ideas of Richardson and actually provide a weather forecast. However, von Neumann believed, I don't know if correctly or not, that the American government is not going to pay money in order to improve the weather forecast. This is kind of, who cares? I mean, tomorrow will be rainy or not, who cares? So he suggested it as kind of weapon, right? What was the idea? The idea was that instead of dropping nuclear bombs on Russia, we can, for example, if we know how to manipulate the weather, we can color the North Pole black by pouring coal or something there, and this will generate horrible tornadoes that will wipe out all the Russians without. So this was the idea that is sold to the authorities, and they actually financed the project. As you may have noticed, the idea of weather warfare of this kind isn't working. The reason was that after doing the best they were able to do, they discovered that they can give weather forecast only for 1 or 2 or 3 days, and then it fails. And the reason for that was discovered by Lorentz in the 60s, that the actual equations are fine, but they are chaotic. And for that reason, you lose accuracy very fast. This was the general story. Okay. So, what's the idea of Richardson? I will show just the first version. So, yes.
נראה לי שאתה לא מוקלט. נראה לי שאתה לא מוקלט. שוב זה קבע.
מה? הם אומרים שאני מוקלט, אני לא...
זה מוקלט שם. לא, אתה לא ביוטיוב.
לא, כן, היוטיוב נדפק, אבל... יש הקלטה אחרת.
אז כנראה יתקנו את זה.
Okay. So, here is I will just show the basic idea. So the basic idea is to say that Fn is L, again, plus A over N. Therefore, Sn plus 1 is L plus A over N plus 1. Right? And this implies that N times Sn minus A is L, but this is also N plus 1 times Sn plus 1 minus plus A. Minus A, sorry. So if you compare this to that, the A cancels out, right? So it turns out that L is equal to N plus 1 Sn plus 1 minus, I guess, N Sn. Yes. So for example, here we want 1.644, right? And we have 1, and so now we have the first Richardson will be 2, so 10 over 4 minus 1. You see? So the first Richardson will be what? Just use these two.
1.5.
What?
1.5.
1.
1.5.
Yes, 1.5. Okay? Much better? Okay. Now if I'm using this and that, how much is that? So I have 2 times, let's say,
The 3 times. It's 3 times this.
No.
N plus 1, no?
No, cannot be more than,
It's N plus 1.
it's, no. I should, this is 3 times 1.366 minus 10 over 4, which is
1.598.
what?
598.
1.598. Okay, you see we're getting closer and closer. Okay, and also here there is a way to improve this by adding here plus b over n squared. Right, and I will, and so on and so forth. Right, you can calculate it by yourself how the L looks like. That's a second Richardson extrapolation and so on and so forth. Okay, so these are, you can think about it as tricks that accelerate the convergence of series. The series by themselves were convergent series. We started with series that were convergent series, but maybe they converge quite slowly, so we accelerate the convergence. However, there is okay. In any case, even if what's the traditional way? The traditional way is to just calculate Sn for large enough n. Again, you may have, even in a convergent series, you may have an anomalous term in the 100 position, right? So even crunching it one by one is assuming something about the rest of the series, and this, once the assumption is actually correct, or once you do not assume only that terms are getting smaller, but also you have the correct way they do behave, one can implement the Richardson or the Shanks to make life better. Okay, so this is part 1, summation of converging series. So there is no problem in principle in simply just summing all the terms, But if we want to get an idea what is going on by summing only part of the terms, this is what people are doing. Good. Now let's think about a much horrible problem, which is the okay. Before doing that, I would like to emphasize an important point. Summation, yes, if I'm 1 plus 2 minus 3 plus 4 is equal to 1 minus 3 plus 2 plus 4, right? Summation is commutative, associative, and distributive, right? And if I have 5 times that, then I have 5 times that, and this will be equal to 5 plus minus 15 plus 10 plus 20, right? Clearly, this is from, I mean, grade 3, I guess, of elementary school. Okay, I can change the order, I can multiply from the outside, no problem. This is not true anymore when we have infinite series. Important note. Right? For example, let's take the series for the log 2 that I put here upstairs, and I would like to convince you that this series equals to, throw a number, 7 pi, right? I want to show you that the sum from n equals 0 to infinity of minus 1 to the power of n divided by n, right? No, that's n equals 1, right? This is a log. I want to convince you that this is 7 pi, exactly. Or any other number that you like. Okay? How to do that?
It is n plus 1 at the power, right?
Hmm?
It is n plus 1 at the power.
N plus 1, yes. So I want to convince you that this is 7 pi or any other number that you want. Okay? How do I do that? Very simple. I'm taking, this is 7 pi. Okay, that's my goal. Okay? Now, I can divide this series into 1 plus 1/3 plus 1/5 plus 1/7 and so on, minus 1/2 minus 1/2 plus 1/4 plus 1/6 and so on. You agree with me? Okay. Now, if I don't have this piece, what is the sum of this series? Infinite. It diverges. This is a diverging series, right? And this by itself is also a diverging series, right? Because if you take 1/2 outside, then this is a harmonic series, right? So this is diverging and this is diverging. So here is the trick. How I will get 7 pi? I will add from these terms. I will add terms until I will get, right? And this is a diverging series. Once I go above 7 pi, I will start taking terms from here until I will get below 7 pi. And then I will try to take the terms from here until I will get up, small up, and clearly it will converge to 7 pi. So I am converging to 7 pi by implementing all the terms in the series, right? In the order that I have chosen.
But you're making infinity minus infinity, right?
No, no. I'm implementing all the terms in the series in the order that I have chosen, and I will get whatever number you want. You want 57e? No problems.
But why you're not doing that? Okay.
So this series converges to any number you like. Not only to ln 2, but to any number you like, provided that you allow me to commute terms. So to say that 1 plus 2 minus 3, to move the 3 to it, right? If you allow me to change the order of terms, I can get whatever answer you want.
אבל למה?
מה?
Why?
Why? Because while addition is a commutative thing, the summation of infinite series is not commutative. Here, I showed you.
Yeah, but why are you choosing the order then?
Because I want 7 pi. Right? So there is absolutely no meaning to the answer I will get if I'm not keeping the order of terms. Very important. What is the condition under which I can change the order of terms and it will not change the answer?
But it's monotonically increasing.
No. I can change the order of term without changing the answer if the series converges absolute convergence. If this is true, then I can use commutation rules as in addition in elementary school addition. But this is not true here. Yes, because the absolute value is a harmonic series and it diverges. Right? So I'm not allowed to change the order of terms. Very important. Right? Once you have a diverging series, not even converging series, but not absolutely convergent series, commutativity is not a feature of addition anymore, so to speak. Okay? The message have absorbed. Good. So once we know that, let's start with a series that is the following: 1 minus 1 plus 1 minus 1. Right? The sum from n equal 0 to infinity of minus 1 to the power of n. What can you say about this series? Yes.
Depends on whether infinity is even or odd, or whether it's even or odd. Because
Is that a convergent series?
I think
No.
not in the.
It
No?
diverges.
Now, what is the definition of divergent series?
No limit that converge to.
A series that does not converge. Right? So this is a divergent series. The partial sums are not going to infinity, but it's a divergent series because it does not converge.
But it zigzags around half.
Yeah, but it zigzags for good.
It doesn't get smaller. Around.
Get 0, 1, 0, 1, 0, 1, 0, 1 for good. Okay, so this is a divergent series. It has no sum whatsoever. Okay? Now, I would like to convince you that the answer is 1/2. That maybe appears to you like a reasonable answer because it's a mean, it jumps between 0 and 1. But I would like to convince you that the answer is 1/2, and I will explain why. First of all, let's define the trick. Right? The trick is called Euler summation. Euler summation. So the trick is as follows. I will say that this series is 1 minus x plus x squared minus x cubed plus x to the 4, and so on and so forth. So the sum from n equals 0 to infinity of minus 1 to the power of n x to the power of n when x is 1. You agree with me? Okay. Now, what is this series?
I know.
This is the Taylor expansion of
Even if it's
1 over 1 plus x. Right? This is the Taylor expansion of 1 over 1 plus x. And if I will plug x equals 1, I
As
will
long as
say
x is not 1.
this is 1/2.
But that is true when x is smaller than 1.
Right? Right? I'm taking x to be whatever I like. And at the end of the calculation, I'm taking x to be the number that I'm interested in.
Okay, but you cannot do that.
What?
You cannot do that, right?
Why I can do that?
Because it's not convergent.
What?
The harmonic series do not converge when x
Wait.
equals 1, right?
This is not the harmonic series. This is not the harmonic series. Right? It's okay. And by the way, what do I want to say? Yes. Okay. Did you understand the trick? Nobody is saying nothing. So what should I understand now? Okay, let's see if you understand the trick. I want to sum the following series. 1 minus what do I have here? Wait. I looked here. 1 plus 0 minus 1 plus 1 plus 0 minus 1 plus 1 plus 0 and so on and so forth. Okay? You see? What is the sum of this series?
It's the same as the first one, no?
Hmm?
It's the
Okay. What's your name?
Oh,
Aaron. Aaron?
yeah.
So Aaron claimed that the sum of this series should be equal to the sum of this series. Why? Because I only added zeros, right? By the same reason that 1 plus 3 minus 4 minus 5 should be equal to 1 plus 0 plus 3 minus 0 minus 4 plus 0 minus 5, right? It's the same thing. However, I remind you that when I did when I'm saying this equals that, I already changed. I can take all the zeros to one side, right? I can interchange. I can write this is this plus 4 times 0, and this is not allowed when I have infinite series.
1/3.
Okay, what?
1/3.
Sorry,
1/3.
1/3. Maybe you're right. Let's see. Okay, I think you're right, but okay. So how did you get the 1/3?
I guessed.
Okay. I thought you okay. So what I want to do is to implement the Euler trick. Right? So let's implement the Euler trick. What I'm doing, I'm saying this is 1 plus 0 minus x squared, right? Plus x cubed plus 0 minus x what? Fifth plus x sixth plus 0 minus x 8 plus x 9th and so on and so forth. Okay? Now, if x is smaller than 1, then this series converges absolutely. Absolutely. You see? The absolute values also converge. So now, when x is smaller than 1, I can happily interchange things here. Yes?
What does absolute convergence mean?
So, absolute convergence means that the sum over absolute value of an is smaller than infinity. So now the series is absolutely converged. And since it absolutely converged, I can write it as sum from n equals 0 to infinity. I'm taking now all the positive guys. So I have 1, I have x cubed, I have x6, and so on. So I will write here x cubed times the sum of x, what do I want to say? Sorry. X cubed to the power of n. These are all the positives. And what are the negatives? The negatives are sum from n equals 0 to infinity of what?
X
Of
squared.
I can put x squared here, and here I can put x cubed to the power of n. So this will give me 2, 5, 8, and so on and so forth. Okay? And now I know that the first thing, right, is 1 over 1 minus x cubed, because this is this series. That's a Taylor expansion of this, minus x squared over 1 minus x cubed, the Taylor expansion of this. Okay? And so all in all, I got 1 minus x squared divided by 1 minus x cubed. And now I should put x equals 1. Can I do that?
No,
Why not?
because it's not absolutely convergent.
What? No.
The two terms.
Now I did all the calculations in the realm where x is smaller than 1 and everything is absolutely convergent. And now I'm taking the limit. Okay? So it's the limit x equals to 1. What I get is 0 divided by 0, and then what I should do? L'Hopital, and what I will get minus 2x divided by minus 3x. So the answer is 2/3. You see, this is implementation of Euler summation trick.
Isn't 2 over 6?
What?
Isn't 2 over 6? Because you have a 1 minus x.
I'm taking the derivative of the numerator divided by the derivative of the denominator.
Yeah, but you have the x cubed.
Yes. So the derivative is 3x squared, and then I plug x equals 1.
Okay.
So I should write here x squared. Yes. I missed this. I apologize. Okay. What's going on here? Let me even be more Now, in these examples that I've showed you, it was a divergent series, but it didn't go to infinity. It just it did not converge, but it didn't go to infinity. Now let's do something which is even worse. So what I would like to do now is to calculate 1 plus 2 plus 4 plus 8 plus 16 and so on. Right? I want to sum, so I want to calculate what is the sum from n equals 0 to infinity of 2 to the power of n. What do you think about this sum? Diverges, right? But let's implement Euler trick. So Euler told us, let's multiply this. So I have 1 plus 2x plus 4x squared plus 8x cubed and so on and so forth, right? And this gives me sum from n equals 0 to infinity of 2x to the power of n, which is, by definition, 1 over 1 minus 2x. Yes? That's power series. And now I will plug x equals 1 and I will get minus 1. So the sum of this series is minus 1. Okay. Now I hope that you are not happy. Why you are not happy? Because clearly I'm taking number plus number plus number plus number plus number, and I end up by saying this is minus 1. Okay? And also what we did here and here looks like, you know, some sort of a black magic. What's going on? Right? We know what the real answer. If it's 1 minus 1, 1 minus 1, it jumps, it never converges. Why? It's 1/2. If I have such a thing, then, I mean, okay, it's 1, 1, minus 1, plus 0, and so on and so forth. Again, it never converges. Okay? So why is this, and why this differs from this? Why this is 2/3 and this is 1/2? What is going on? So, first of all, it's a fair criticism. Right? Second, and this is something, a very important message that I would like to stress. There is something called a function, right? A function is 1 over 1 plus x. This is a perfectly kosher but that certified function for every number except of x equals minus 1. Okay? This is a perfect function. Now, for x equals 3, it's 1/4. No problem. Right? Now, I'm trying to expand it in a Taylor series. And I'm writing that this is 1 minus x plus x squared minus x cubed and so on, so on, so forth. And now if I plug x equals 3, I will get garbage. It will never converge. Or if I will plug x equals 1, I will get this series, the 1 minus 1. Okay? So here is the way we should think about that. There is the function. The function is not this. The function is not that. These are representations of the function that help us in calculating numerical value. The function is a Platonic idea that lives with God in heaven, right? And what we can see in our nasty world is only representation, I mean the התגלויות, I don't know how to say that, of the function, right? We can only see, we humble creatures, the way the function reveals itself to us. And it reveals itself to us via such things, okay? Either via series or via expression like that, or I don't know, in our dreams, I don't know, but these are the ways that the function, the holy function reveals itself to us, right? Now, some types of appearances, of such התגלויות, are not good enough. So, for example, this type is good when x is smaller than 1. But when x is larger than 1, it's not good. What Euler trick allows us is to take this bad representation of the function and recalculate and suggest another presentation of the same function that will be maybe good. Okay? This is one thing. So, I mean, this is a very simple example that shows you that the Taylor series may diverge while the function is absolutely, perfectly, nicely converged. And this is another, right? So the idea is that when I'm doing calculation, perturbation theory, when I'm doing all kind of local and global analysis, and I'm finding such a horrible series, right? I'm not telling myself, well, this implies that if I'm taking a harmonic oscillator and put anharmonic perturbation, it will explode and kill all of us, right? No. It just implies that I'm getting a bad representation of a very good, nice, fancy, smooth function with derivatives and so on, right? And the Euler trick is a trick that try to allow us to guess. It's a kind of a guesswork. You have a series that diverges, and you try to guess what is the underlying function, good function, non-diverging function, that yields such a series. That's the interpretation of Euler summation. Yes?
Why can't we say that 2 to the n function goes to infinity? Why do we have to do this Euler summation?
Again, if you have this series given you from your teacher in the 3rd grade, then you're saying, well, in calculus, the numbers are going, I can't stand it. It's diverging. It goes to infinity. The answer is infinity. Okay? But if this is the kind of series that you get when you calculate the anharmonic correction to the energies of a harmonic oscillator, you know that the anharmonic oscillator do not have infinite energy. It will have finite energy ground state, right? But you have diverging series. So you are saying, okay, so I don't know what is going, I have a diverging series, let's try to, what I believe that this diverging series is not that it have the ground state of the anharmonic oscillator have infinite energy, but it have finite energy, and there is a nice function whose series representation is wrong. So let's look around for functions that gives the same series expansion, but they are absolutely good, like 1 over 1 plus x. That's the logic. Right? So when you're doing Euler summation, you start thinking like a physicist. You're saying, well, no, this series cannot diverge. Okay? So I should sum it Euler. Okay. Okay, now I would like to give you another example, which is, okay, another power series. 1 plus 2, not power, another series, plus 3, plus 4, plus 5, plus 6, and so on. So the series is sum from n equals 1 to infinity of n. Okay. And now I want to implement Euler trick. What I should do? I replace it by 1 plus 2x plus 3x squared plus 4x cubed, and so on and so forth. Or I can write the series as the sum from n equals 0 to infinity, 1, sorry, to infinity of n x to the power of n. No, so this will be
n plus 1.
n plus 1 to the power of n.
N plus 1.
X to the power n minus 1.
Or n power n minus
well,
1.
Okay. Is that fine?
If you sum it from n equals 0 to n.
Okay, no. I would
N.
prefer to have it from n equals 1 to infinity of n times x
Plus
to
one.
the power of n plus 1.
It's n minus
N
minus 1. Then the
minus 1.
the derivative of
What?
the-
What's going on? No. I will.
Yeah, it's a
Sorry.
derivative.
No.
Yeah.
Okay. Of course, there is absolutely no. What I would like to do is x plus 2x squared plus 3x cubed. Is that what I want to do? Yes. Yes, this is what I want to do. I mean, of course, there is absolutely no difference. Okay? So what I have here is the sum from n equals 0 to infinity of n x to the power of n. Note that the first term in this series is 0. Right? But all the others are perfectly fine. Right? 1 times x to the 1 times. What am I doing here?
So 0.
It's fine.
Yes. 0 times x to the 0 plus 1 times x to the 1 plus 2 times x squared and so on and so forth. Okay. So it's not exactly Euler, but simple variation of Euler. Okay? And now what is that? What is this sum? How to sum such a sum?
Take the derivative.
Very good. So I want to write that this is x ddx of the sum of x to the n from n equals 0 to infinity. Because the ddx will take n to here, and this will be n minus 1, and then I multiply by x. So it will be the same thing. And this is 1 over 1 minus x. By definition, so I have x ddx of 1 over 1 minus x. Now, the ddx of 1 over 1 minus x is 1 minus x squared. I have two minuses. One from the fact that I'm taking the derivative of the denominator, and the other one is from the minus x, so they cancel, it's plus. So at the end I have this. Right? And now, according to Mr. Euler, what should I do in order to get the answer?
Plug 1.
Plug x equals 1, right? And when I plug x equals 1, what I will get?
0. 1 over
Infinity. So this was an important exercise that shows you that Euler is not a magic remedy to everything. Right? Some theories diverge even after treated by Euler trick. Right? So this implies that Euler is a guesswork. Euler is not. I'm trying to guess a function that yields this series as a bad representation. But so if I'm getting such a series from calculation of perturbation theory of some kind, then I'm trying to guess a function, and I find out that if I'm trying to guess a function with Euler, I cannot do that. You see, I'm trying to guess a function. If I'm trying to guess a function using Euler, it will fail. Right? So, what one should do, again, if you are a physicist and you obtain such a series, right, then you should believe, right, since you know that the world do not explode under the perturbation, you should believe that there is a function that give us this power series as a representation, and the function is good. It's a series which is bad. And I have to guess one. But I tried Euler, and I find out that I cannot, Euler do not give me the correct answer. Right? So here is another trick. This is just to entertain you. So please agree with me, okay, that, please agree about that, right? The first trick that we, the first result that we, that one, I call it now S1, do not, this is some number one, not has nothing to do with Shanks or Richardson or whatever. So S1 implies that 1 minus 1 plus 1 minus 1 plus 1 minus 1 is 1/2. If you purchase this garbage for me, right, then I can define S2 to be 1 minus 2 plus 3 minus 4 plus 5 minus 6, right? And the trick will be that I will add another S2, which is 1 minus 2 plus 3 minus 4 plus 5. This is the way I add them. I add them with a shift of 1, right? So what I obtained is that 2S2 is equal to what?
1 minus 1.
1 minus 1 plus 1 minus 1 plus 1, and this is 1/2. Right? So S2 is equal to 1/4. Okay? Now I would like to speak about my series. So S3 is 1 plus 2 plus 3 plus 4 plus 5, and so on. Okay? And I will add S2. I will subtract S2. What will be the result? One minus 1 is 0. 2 plus 2 minus minus 2 is 4. So I have 4, this is 0, this is 8, and the next one will be 12, and so on.
4 times.
Now this is 4 times what? Times S3. So what I obtained is that 4S3 equals to S3 minus S2, but S2 is 1/4. So 3S3 is minus 1/4, so S3 is minus 1/12. This is a result that people have mentioned before, right? So when physicists arrive at a perturbation theory that gives them this series, okay, they are saying, okay, and the sum of this series is minus 1/12, right? And there is a physical problem that yield this series. It's, how do you call it? Casimir effect, right? So the Casimir effect is, you know what this effect is? If you take two closed plates, let's say metallic plates, then the electromagnetic field between the two should satisfy zero boundary conditions, right? And if you take them farther apart, it will have more energy. If you take them closer, then of course you have less modes, so you have less electromagnetic energy from the vacuum. The vacuum energy of the electromagnetic field will be smaller and smaller, and that's why there is a force, that attractive force, acting on these two plates, right? So, or for example, if you have, there is a principle of people in harbors, nemalim, not to put two long ships next to each other, because that's exactly the same. It generates force due to the water waves that are between them. It generates force that will stick them to each other. Okay? So this, and the calculations of the Casimir effect are leading to such series, and when people are arriving at such series in perturbation theory, they are saying, okay, this is minus 1/12. Now, this is not Euler, as I showed you. So the name of this is actually the zeta function of -1, right? Because the zeta function of x is the sum from n equals 1 to infinity of 1 over n to the power of x. So this is, yes, so this is the zeta function of -1. And the zeta function of -1 is indeed -1/12. So this is called zeta function regularization, right? So it's yet another way of a guesswork that allows us to guess what is the actual correct function that yields the ugly, what is the nice function that yields the ugly power series. Okay. And last word, I wanted to show you also Borel summation, but this will be next time. Okay, it's just 5 minutes. Lastly, I would like to explain how come that 1 plus 2 plus 4, I mean, again, this is a growing and growing and growing, all the partial sums are growing and growing and growing. Why we end up with -1? How can we understand that, right? So the way to understand maybe is a big word, but the way to make it to get some, who knows, to get it close to our mind, right, is to think about it in the complex plane. And the point is that in the complex plane, infinity is a point. You should think about the complex plane as a sphere, actually, where infinity is the north pole and 0 is the south pole. And therefore, if you add numbers, right, you go dang, 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 then it goes to infinity and to -1, right? So the real number axis is not like that, but actually like that, right? And you start here, you add numbers, blah, 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 and this is infinity, you end up here, or whatever you like. Right? That's it has to do with, I guess, what you were taught in, who knows what here, which is analytic continuation. In what course they teach it? Memphis 4? Okay. So this is actually all kind of analytic continuation, because in analytic continuation, you know what you are saying is that you may have, if you have a function that is defined somewhere in the complex plane, and then you have another function which is defined only here, if they are equal on the common domain, they are the same function. So the extension is unique. And to some extent, what you are doing here is to guess the extension. I mean, this function is not going to diverge here, but you guess, the guesswork gives you the extension of this function to the other parts of the analytic of the complex plane. I'm not pretending to understand it myself, so I'm not asking. I mean, maybe you understand it better than me, but this is the basic idea. The important thing that I would like you to grasp is that perturbation theory gives us power series, which is if you plug number, it gives us a series of numbers that you have to add up. In many cases, adding up these numbers is a lost cause. You're not going to get anything useful. In order, but on the other hand, as a physicist, we know that it should give something good, right? We know that the ground state of the anharmonic oscillator is some number and not infinity, everything explodes.
Unless you're doing quantum field theory, right?
Even if you are doing quantum field theory, right? So we know that there is an answer, we get some horrible power series, and then we are saying, okay, we would like to guess the right function that yields this ugly, diverging, whatever like bad words, power series. And the way to do that is to use some sort of regularization or something like that, that will give you, or like the earlier summation, that may suggest a right function, and you have earlier summation, so you have zeta function regularization. There are many types of regularizations, but no, I don't know if so many, but there are a few types of regularization, and it's a kind of organized guesswork as for what is the function, actual function that yields the garbage that we get, right? Okay. So this was what I'm going to do next time. First of all, I would like to show you how to do Borel summation. So the Borel summation is like Euler summation, a little bit more, adding some little trick, but essentially it's the same thing, very close. It may work even when Euler do not work. And so this is Borel summation, and then we are going to speak about the real black magic, which is the Pade approximants. But this will be next time. Thank you very much.
Thank you. Thank you.
איפה עובד? איפה למטה עובד? הבנתי שיש לזה שימושים... זה לא יפתיע, זה...
מסמכים ככה אינסופים. כאילו זה... משתמשים לזה לנורמליזציה. כי אז אתה מקבל את סוף. כאילו, יש... אני לא יודע למה, יש כל מיני תחומים פיזיקה שאתה מקבל בהם אינסופים, ואז יש כאלה שאתה יכול לסלק ויש כאלה שאתה... וככה מספרים שיטות האלה. אז אתה מנרמל את זה ביחס לטור הזה, ואז זה לא מתבדר לך. כי באופן קלאסי זה מתבדר אותו. נראה לי, כן. פעם קודמת הדברסתי.
אני פשוט שונא להשלים.
כן, אני שונא להשלים. אז זה, אם אני לא...
מה זה האומץ הזה?
זה לא אומץ, אני קוראת את המערכי שיעור, רוב המתרגלים פשוט מכירים את המערך שלהם.
לא, אני איתה בסך.
אבל קשה ללמוד ככה.
אז בהרצאות אני בקושי משלים.
באמת?
פספסתי, זה החיים. מה זאת אומרת?
לא, הרצאה אני אשלים.
לא, תלוי איזה.
כן, הרצאה אני אשלים, אבל תרגול אני לא אשלים. כאילו, אם אני לא מגיע לו, אז אני לא מגיע לו בידיעה שאני לא אשלים.
אני לא אשלים את זה בבית, זה נורא.
לא, זה ברור שכן.
אתה סיקור זה פעם.
אני עשית את זה. כן, אני חושב ככה, אבל לא הייתי רוצה.
מה שאנחנו עושים
המנהג הברברי הזה שלו בזמן?
אני התחלתי אותו. כן, אני המצאתי את זה, מה זאת אומרת? רגע. רוצה להתרשם מהסיכום ההרצאה שלי?
איך אתה מצפה שהתגובה שלך תהיה?
תקפצי מאחר מבושת?
לא, אני כזה תדהמה, גסים.
איזה יפה. מסודר, מפורט, עברית.
לא שמעתי זה שיין ביזנס סיריס.
שיין.
שיין זה טוב.
נכון.
שיט.
איזה יופי. אפילו.
טוב, אני חושבת שזה מקשיב. איך זה צריך ליצור טבלה באמצע? זה צ'אט GPT.
זה הג'מיני, אבל אני לא יודע מה לעשות. כן. איזה מסודר, זה יפה. 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 הכל פה. לא, אבל רוצה לראות באמת משהו אנשים? זה פה. זה יצא לי ממש יפה. זה ההרצאה האחרונה באמת.
כן, באיזה, תשלח לי.
כן, נשלח. חכי, תראי את זה. נכון. נכון. הכל. כן, כתוב גם את המשקלים. הכל. וואו. כל הרגל מפורטת, צעד. בלי דיוגים, בלי כלום. ועוד גרף.
זה מרגש לי.
אפילו יש חצי מה המרחק. ו... אפילו לא אמרתי לו שזה זה המאגר נתונים הזה. כן. נכון, זוכר שהוא צייר את הספרה 3 קדימה. לא ראית אותה גם? לא, זה שני. ספרה שאתה נכון. זה נגיד, אין לי כוח לתקן
Okay, hello everyone, let's get started. Today we're gonna cover some interesting topic. I mean, the first one is just a summation of the series. We will see how you can increase the speed of the convergence of the series, and the second one is more sort of a magic. We will learn how to sum divergence series. But we're not actually gonna sum them. We just assign some number to the series. Okay. Firstly, we will define what is a convergent and the divergent series. Okay. So, for example, we have some series. Okay. We can define partial sum as n for this series, right? So we just not take infinite amount of terms, but some number n. Okay, and if there is a limit, then n goes to infinity of partial sum. It's just some s, right? Some finite value, then we can say that this particular series is convergent and everything is fine. The second type is divergent series, also known as asymptotic series. Usually in physics, we work with the second one. So let's define the series n x power n. Okay. So we call this series asymptotic to a function. Asymptotic to the function f of x as x goes to 0. And we can write this as using familiar symbols. So this series asymptotic to function if for every fixed truncation order n, the difference between f of x and the partial series this form is order of x plus 1. So more simply we can say that asymptotic series diverges in the general sense, but we can define some order of truncation that the error will be minimal. Okay, so the difference between those two here, if we increase n, the error decrease, right? And for asymptotic series, we need to find particular truncation order to get the minimal error, because starting from the n that's bigger than this, the error of the of this series will become to increase. Okay. So these are just definitions. Now let's do some practice. So the first, we will talk about the Shanks transformation. In this transformation, we will assume that our partial sum goes like this. So this is the actual sum of the series, and this is just some error of calculations for the n. I think it should be, should be the same one, like this. And I think on the lecture Nadav showed you how you can calculate the beta estimation for S of n, right? So you just need to use three terms, Sn minus 1, Sn, and Sn plus 1. So firstly you calculate those three partial sums, and then you do some algebra and derive this new chunks estimate. So it looks like Sn plus 1, Sn minus 1, minus Sn squared, and in the denominator is Sn plus 1 minus 2Sn plus Sn minus 1. So this is our formula, and we will do it. Let's start with something simple. Let's calculate number pi. I know that there are a lot of ways how you can calculate pi, but we will use one particular method in which Schenck transformation will be applicable. So let's firstly write the Taylor expansion of arctan. Do you remember the expansion? Taylor expansion? So it's minus 1 n x 2n plus 1 divided by 2n plus 1. Sum goes from 0 to infinity. Why do they need it? Because we know that arctan 1 is pi over 4.
This is not tangents?
It's arctan. So the inverse of the tangent.
Yeah, I just remember it for tangents.
So arctan 1 is pi over 4, 45 degrees, right? The angle. And if we calculate this up to 6 digits, it will be 0.785398. Okay. So now we can use this series to calculate also pi over 4, right? Because now if we plug in x equals 1 in this series, the sum of the series should be pi over 4, right? It's the same thing. So for x equals 1, our series is just minus 1 to the n divided by 2 plus n, 2n plus 1 from 0 to infinity. Okay, so it's 1 minus 1/3 plus 1/5 minus 1/7 plus 12. Yeah. So let's calculate partial sums. Okay. So S is just first term, right? Then S1, we pick these two. It's 2/3, right? Or it's 0.6667. Then S2, pick 1, 2, 3, this, and we will get 0.8667. So you can see that after we sum these three terms, we still didn't achieve the accuracy of 10 to the minus 1, right? The first digit after a point is not the same. So the question is how we can achieve the accuracy of 10 to minus 6, as we see here. In fact, we need to get around this number of terms of the series, but it's quite a big million terms to calculate to get this estimation. Okay, but what if we don't have enough time or patience to calculate million of terms? We can use this formula, Shank's transformation, to improve our results. Okay, so basically we will estimate u as 1. Estimate u as 1. And using this formula should be s2 s0 minus s1 squared, s2 minus 2 s1 plus s0. Okay. Then we plug to this formula all of these numbers, and eventually we will get 0.7917. Okay. So now, from this step, we get much better accuracy to, at least we get the correct, the first digit, right? So, and again, we can, to even more improve our estimation, we can do the same procedure, right? We can calculate S3, S4, right? Then we can estimate S3. Actually, we can estimate also S2, and S3 with this formula, right? And then, to even better improve our results, what we can do, we can apply this formula again, but for these values. Understand what I mean? No? Yeah, good. So
can we do this like multiple times?
Yeah. I mean, we actually here is just Shank's ordinary Shank's transformation, and here we got Shank's estimator. When we do it 3 times, we can do Shank's of Shank's, right? So I can I don't know, define S, let's call it Sn double head, okay, and we'll use this formula. These are just Shank's transformation, and this is even better. Okay.
But there will be a limit for the error. Like we are, I mean, we are minimizing the error each time we do the Shank's, right?
Yeah, we actually we're not minimizing the error. We just improve our accuracy. Okay. So.
What is the difference?
Yeah, it's the same. Okay. Yeah. So every step, yeah, it's improved. Okay. Good. So the second example, we'll connect it with statistical mechanics. So from physics. We will try to understand how we can apply Shank's transformation to the question how we can find the critical temperature. of the phase transition. Okay. So let's imagine that we have 2D IC model. So square lattice, just the sides of the spin. And spin has two directions. It can be either up or down. Okay. So we can write the Hamiltonian of such system. So J is just a spin coupling constant, and for instance, should be greater than 0 means that our system is ferromagnet. Okay, these brackets means that we interested in only nearest neighbor interaction. So this spin can interact only with its nearest neighbors. Okay, there are 4 neighbors. Okay. The spin cannot interact with this one, only through other spins. Okay. Also, in the system, there is no any external field, so there is no magnetic field, and we want to find the critical temperature. You know that in the 1D IC model there is no phase transition, only in 2D and above, so 3D, 4D dimensions. So what is the phase transition here? It's just transition from ferromagnet to let's this. M is magnetization. Here is some critical temperature. So below it there is some net magnetization, but above it it's 0. Okay. So in this region there is a magnet. In this region it's called paramagnet. So no magnetic features. Okay. So how do we usually begin to solve any statistical mechanics problem? What should we write?
Partition function.
Partition function. Good. And the partition function is something exponent in the power of the exponent. It's Hamiltonian, right? So z partition function e to the minus b minus beta h, right? And eventually, if we plug this Hamiltonian to the exponent, we'll have this term. K S I S J. So K is just a shortcut for this one. So what is the value of this multiplication? SI
SJ squared. Oh, wait, SI/SJ or
yeah,
SI?
they are different.
Oh.
So there are in principle 2 values, right? If SI and SJ looking at the same direction, either up or down, it's just 1. If they are in the opposite direction, it's minus 1. Okay. So this just plus or minus 1, and we can use sort of a earlier formula for this real exponent. it's the same like for the imaginary exponent, but with hyperbolic functions, right? So it's the hyperbolic cosine of k, yeah, k, then plus SISJ, hyperbolic cosine of k. Again, this term is just plus or minus. Okay? So if it's the multiplication is -1, the hyperbolic cosine minus hyperbolic sine. If it's plus, so just 1, and this is the sum of these two functions. Okay. When I can do this. And this is just a hyperbolic function. And I call it omega. So we know that omega is a function of k, and k is a function of temperature. Right? So basically, we see that our partition function is a function of temperature, right? And the same true for magnetic susceptibility. So we call it I. Magnetic susceptibility. We can define it as this. Basically, we're looking at correlation between pair of spins. So let's call this spin is S0, okay? And we sum over different pairs of spin. We're looking for how they correlate with each other. And so basically, magnetic stability shows us how system behaves under magnetic field. Okay, so if the magnetic stability is huge, then if we apply magnetic field, the system is magnetized very easily and fastly. And that means that spins are very correlated to each other. So in the sense that this spin can easily communicate with this one and even with this one. Okay. So, but we need to understand how the magnetic susceptibility behaves with the change of the temperature, okay, of omega. So we expect that for the high temperature is somewhere here. So for T, much greater than T critical. Right? K is much smaller than 1. Right? And this is also something small. So we can say similar things for omega. But again, from statistical mechanics, we know that magnetic susceptibility behaves like this. So at t equals t critical, it blows up to infinity. Okay. So we need to use it, to use this knowledge to find this critical temperature. How we can do it? We can assume that there is an expansion of time. Okay. So, because it depends on omega, we can say that there is this expansion. And then this omega going to critical temperature, this expansion blows up. The question is how we can calculate these coefficients of the expansion. This is really hard and not non-trivial problem. We are not actually going to. I will not provide you bulletproof how to calculate these coefficients, but instead, let's do some sort of a how do I call it? Yes, sort of a toy proof. I would say that these coefficients they correspond to correlations between spins, and for order of omega to the power of 0, we're looking at this spin, okay, and this is the only one spin, and the correlation of a spin to itself is just 1. Okay. So therefore, we write that A naught is just 1. Then we go moving forward to the order of omega. So in the sense that we are actually now going one step forward. We're looking to the neighbors of this S naught. How many neighbors of this naught? Just 1, 2, 3, 4. So there are 4 possibilities how this spin can correlate with these neighbors. That's why A1 is 4. Okay. Then the last order of omega squared. So we did one step to, let's say, to this neighbor or to this, doesn't matter. So now we are here. Okay. Again, how many neighbors do we have? We have 1, 2, 3. Actually, we can go back, but
we already calculated this. When the middle one interacts with the upper one.
Yes, we're interested only in the paths that are going to the same point, but not. So we don't need crossing the same point. Okay? That's why then we did one step forward around the 3 options with which spin can correlate. Okay. Then A2 is just 4 options that we had here, right? Multiply by 3 options in the next step. So it's 12. Okay. Again, we can calculate other A3 and 4, but again, it's really complicated, okay, because you need to encounter all of the possibilities. So, but now we only have 3 terms, okay? Just 1 plus 4 omega plus 12 omega squared plus something else, okay? And we want to some sort of sum this series, but we only have these 3 terms. I mean, we can take this as an answer, but why it is bad answer? Just say, if we say that this is our sum.
Because if it's diverged.
Yeah.
So
In this case, there is no option how it can diverge, right? I mean, because we know that this should be finite, okay, some finite number. But we can use Shanks, right? We have 3 terms. Right? We have S naught. It's not just 1. We have
Shanks is for converging series, no? Shanks is not for converging series.
For conversion, yeah.
But we just said this should be the.
For now,
Like we're saying the susceptibility should they?
yeah. We expect that at some value, it will diverge. Okay. So, but for now it's we just calculated some partial sum of series. Okay. 12 omega squared. Okay. Then we can find S1 hat. Okay. We just need to use this formula and plug in these values. So what do we have? S2 is 12 omega squared multiplied by S, not just 1, right? Minus 16 omega squared, right? And here is 12 omega squared plus minus 8 omega plus 1. Okay.
S1 is 4 omega or 4 omega plus 1?
Oh yeah. Yeah, I did something. Everything wrong. Yeah, thank you. So, of course, should be this and this. Yeah, thanks. Therefore, it will be different expression. Let's see. That would be 1 plus omega 1 minus 3. This is our estimation for just using first 3 terms. Okay. So the only way to find the critical temperature is say that magnetic stability divergent. So there is only one point, omega equals 1/3. Okay. This point, this is actually critical temperature. I mean, you can go back to the temperature and derive the critical temperature in other terms, but you can use omega as well. And actually, mean field if you know this approximation, gives the same result for the critical temperature, but the
Wait, why is omega equals 1
because the point there denominator is 0 is omega equals 1/3. And they say that at critical temperature, magnetic susceptibility should go to infinity, should diverge, okay? And the only case that this expression diverges is then omega is 1/3. Okay, so if you do the same, if you will explore the same system using mean field approximation, you will get the same number, but the exact solution of 2D Ising model is actually a bit different. Exact solution of the critical temperature. It was done by Ansider, and he calculated that critical temperature is actually 0.41. So here we have 0.33, and the exact solution gives us this. Good approximation for the first time. So any questions about Shank's transformation? Okay. Now we're gonna learn different technique, which is called Richardson approximation. This is something else. Extrapolation. Okay. How do we usually use numeric analysis? For example, we don't know how to solve some differential equation, it could be nonlinear, and we want to ask a computer to solve it. How do we usually do it?
Set initial conditions.
Okay.
Make it or the steps.
Yeah. So computer cannot manipulate with functions as a continuous variable, right? Because you know that in the here is an infinite number of numbers. Yeah? So that's why if you have some function, like this, okay? T or X, whatever. Computer cannot treat this as a continuous function, right? We need to split our x-axis to some make some grid. Okay? Now this would be x0, x1, and xn. And then we define function at each point. Okay? So from f of x as continuous, function, we go to f of x n. So we will have some set of values of f. Yeah. Also, we can define some step h, right? And usually to get better approximation, we just simply can decrease the step, right? To get more information about function in these points, right? So, but sometimes it's too expensive to increase the step, and that's how we can actually go to Richardson extrapolation. The core idea is following. So you have some approximation that your computer calculated, and we assume that this approximation is exact answer plus some errors, right? And we say that these errors depend on step, okay, in some power. This we call leading order error. Yes. Yeah. And this is next. How we can improve our approximation? Simply, we can choose lower step, smaller step, okay? And therefore, our approximation will be exact answer plus something smaller than we had before, right? But again, it will not improve the order of error. So the question is how we can eliminate this term. We can define the same thing, but for half of the original step. And then using some basic algebra, you can find that the formula for L. So the exact answer is approximately this. Forgot to mention that P is the some unique value that depends on the method that you use. So P is just some number. Usually, yeah, it's, we call it order of the method. So by using this Richardson extrapolation, you will get better approximation of your function, of your answer. Okay, and it will have next error order, because by using this we eliminate this p order, and that's why only the next order I will have. Okay. So let's practice with the Richardson extrapolation. The first example will be the derivative of the exponent. So let's imagine that we have e to the x function. Of course, we know the derivative of this function, but usually we will try some methods with known functions and then apply them to things that we don't know how to compute. So when we want to calculate f prime of 0. We know the exact answer is 1, but let's try to use numerics for this. Okay. So let's find d of h. So it's the first derivative of function with step h. So we will use forward difference. So f n plus 1 minus f n divided by h. This method of defining derivative has leading order of error term just h. Okay. So in our case, for h point 1, we need to take function at the first point and subtract function from point 0. Okay, so it will be e to the h minus e to the 0 divided by h. Okay. So this is my 0 point, this is h, just one step. In our case is 0.1. Then we can plug in 0.0 and but how we can calculate this one, the exponent? We can use Taylor expansion. Right? So the Taylor expansion, and yeah, so it's 1 minus okay, this is the answer, and we know that exact answer is 1, so this is our error calculations. Okay. If you want to improve the result, we can use half of this step. So h is 0.05. In this case, we do the same calculation. We will get 1.02542. Now we a bit improve our. Actually, you see that improvement is about 2 times. But now we can use this Richardson approximation, right? Calculate, because we have our estimation at the half of the step and the step itself, and we know that order of the method is
Just 1.
so using this formula, it's 2. Then we plug in this minus this divided by 1, and we get 0.999. So if in this step the error was approximately 2.5 to the 10 minus 3, in this case approximately 8 to the 9. And here is error approximately okay. So by dividing the step by 2, there is no big improvement in the error. So the order of the error is the same. But then we apply Richardson approximation to our scheme. We got the beta error. So the estimation now is we have smaller error than in just simple formula for the derivative. Okay? Any questions? The next example is for the integration. For the integration, so let's imagine that we have this integral that we cannot solve analytically. So we go into PC and try to numerically calculate this integral. Again, there are a lot of ways how you can calculate numerically integrals. There are a lot of schemes, but let's look at this one. We call it trapezoidal TFH. Our true value of integral plus C1H2 plus C2H4 plus etc. And you see that this method is second order, because the leading error term is in the second power. If we use this Richardson approximation, we can get the new formula. So it's t to the second power. Excuse me, to the second power, because there is the p equals to then ch2 minus ch divided by, or let's write it like this. And using one step of Richardson, we can get this method. And this method is the leading order, because we eliminate leading order of this. This method has leading order of 4. And basically, if you got numerics analysis course, you know that this is just another way how you can integrate, calculate integrals numerically, and it's called Simpson rule. Okay, and actually you can do the same thing as you did for Shanks. As we remember, we can do Shanks of Shanks, right? Here's the same logic. You can do multiple times Richardson approximation to get the beta approximation. Okay, so in this step, you get the leading order of 4, but if you calculate the same thing again, you can get the next leading order of 6. And that's how we can improve your calculations. Yeah. So for the convergent series, this is it. Now, if you don't have any questions, let's go to the asymptotic series, or just divergent series. No questions? Okay. So usually in physics we dealing with series of this form. Okay, and in some cases the coefficients of the series behaves like factorials. But again, we want to sum this series. Okay, find some answer to physical problem. How we can do it? We can use so-called Fourier transformation. So we need to remember the definition of factorial. I mean, not definition, but one of ways how you can write the factorial. You can write it as a multiplication of numbers from 1 to n, but another way you can treat it as gamma function. Right? Okay. So, and there are 3 steps of word transformation. And the first step, we define a new series. So basically, we just take the coefficients of the original series and divide them by n factorial. So this is new series. Okay. The next step is to integrate, because we divide our original series by n factorial, we need to multiply by n factorial, right? So, but for the n factorial, we can use this definition. Okay, and then our real sum sometimes you can find it or sum in this way. So you just change the order of integration and summation, and that's how you can, you know, find the sum of divergent series. Then coefficient of the expansion goes like factorial. Okay. Let's look at the example. The first series will be the following. So minus 1n and factorial x to the n. Okay. So as you can see, because there is a factorial for every positive x, this series will diverge. But we can try to sum this series using parallel transformation. So again, for the first step, we define new series. How? Just divide this series by n factorial. So new parallel series, just the old one, divided by n factorial. So just minus 1 to the n, z to the n. Okay. So we can rewrite this way. Now we see that this is just geometrical series. So, and we know that the sum of this series is this one. Okay. So, therefore, we borrowed sum of the original series. It's just 1 over x integral e to the minus t of x 1 over 1 plus t. So if the only problem is that in t equals minus 1, the denominator can be 0 and this goes to infinity, but we integrate over positive x's, so that's why that's totally fine. And you can, for a particular x, you can calculate this integral numerically and get some answer. So basically it will be the answer for this series at particular x. Okay? So, and the tutorial I wrote that for x equals 1, the finite value that we assign to this divergent series is 0.596. Okay. Questions?
The last step you do it numerically by computer, or you use the last
No, you cannot solve this integral analytically. That's why you need to plug in this computer and from
So you don't use the Euler summation or Euler summation?
No. Euler summation is only for the series that A. So then these terms is not growing like factorial.
No.
So if the terms of the series going like factorial, you cannot use this type of summation. Okay? Only Barrett summation. Okay. Then I also have some physical example. So this is just Hamiltonian of oscillator, 1D oscillator. Okay. And we know that the solution, we know the spectrum of energy, eigenstates, and so on. But the question is, what if I add additional anharmonic term? How my energy states will change. So, and G is some small number. To find this, we need to use perturbation theory, right, as we usually do in quantum mechanics, to calculate the new energy states. And one can show that using perturbation theory, you can find that new ground state will look like this series. Okay, and these coefficients, the expansion, will for large n will behave like this. So even though we have here some function that goes to 0, then n goes to infinity. If we multiply this by n factorial still grows much faster than every other functions. So that's why this is asymptotic series and it's diverges, right? But we know that ground state energy is finite, right? It cannot be infinite. So that's why we need to somehow assign a new value for this divergence series. And because coefficients grow like factorial, we will use Barrett summation. So again, in the first step, we need to define new series. This one, yeah. Just divide these coefficients by n factorial, and in this case, we'll have -1 and +1, 3 f's, n, t. And again, you can simply treat this as a geometrical series, right? And the answer is 1 plus 3/4t.
Shouldn't there be a minus?
Because of this. Yeah?
Because of the +1.
Thanks. Okay. And then the eigenstate, the original sum. Just there are some other terms. Why? Because this is approximation. So this is only true for large n. For small n, it's not true. And that's why there is some additional terms for smaller n, but they are fine. They don't do this integral divergent. Okay. So again, you can plug your favorite value of g and calculate this integral numerically and get the new value of ground state, okay, for unharmonic oscillator. Good? Any questions? Okay, now the final topic is error summation. So, for example, we have this term, this series. And we want to sum the series. For example, it could be this kind of series or other, yeah. And the question is how we can actually sum this. We need to use which is called error transform. We rewrite this series in this way. What is the delta? Delta is the difference operator. So it's, if we act this operator to
PK then,
n,
the summation.
oh, should be n, yeah, thank you. So it's just n, a, n plus 1 minus a n. Okay. So we don't have time to get this to derive this formula, but you can see the derivation in the tutorial. So let's use it to sum this series. So we have this kind of a series. We want to sum it. So 1 minus 1 plus 1 minus 1, etc. On the first step, we define a naught. A naught is just first term, it's 1. Okay. Then a1 is minus 1, and we want to calculate the difference of a1. So difference of a1, sorry, a naught, just a1 minus a naught. So it's 1 minus 1, 0. Okay. So if we rewrite this series in these terms, we have 1 half
Minus 2. Minus 2. 1 minus 1 is minus 1 minus 1 is minus 2.
guess I have a mistake in the tutorial notes. I need to fix it. Okay.
Still works.
So the first term will be just because this operator in the zeroth part just identity. Then minus 1 over 4 delta A naught, then plus 1 over 8 delta of delta A naught, and so like this. We calculated this one, so just 1 half minus this is 2 minus 1 half. Right, there is a plus, and here is a 2 different separating, so it would be second. Yeah, in the derivation notes, there is a shift operator. Then I act this operator to an, I get an plus 1. So and then I can define delta difference operator using this one. So in this way. Okay, because if I add difference operator to this state, I should get an plus 1 minus an. Right? So this is from one side. From another side, I can act this to a1, an, and then I act this to an. I get the next value minus 1 an. So it's basically the same. And then we want to understand how delta squared works of a naught. We need to square this. So it will be e squared minus 2e plus 1. And therefore we have a2 minus 2a1 plus a naught. This is our delta squared. Let's a2 is 1. Okay, so 1 minus 2 plus 2. Here is plus. It's 4, right? And I will have 1/2. So these are cancelled out. I have 1/2, but I need to calculate other terms, right? So I'll check my notes, and I think I missed something here, so I will upload the notes with the corrected version of the class. But you know that this sum is 1/2. Yeah. This one. Yeah, so we don't have time to look at the Casimir effect. You can look at home. It's pretty interesting example where we can use Euler's summation in physics. So we know that what is Casimir effect is then you have two plates that can conduct electricity, electric current in a vacuum. Okay, there is a vacuum. In the experiment, scientists got that these two plates will attract each other in vacuum. So this is strange. No? I mean, there is no anything except these two plates, and somehow they conduct into each other, attract into each other. And in the tutorial you will see how you can derive this and how you can sum the infinite energy of vacuum. Okay, so that's it. Thank you. If you have any questions, please ask.
Thanks. Mellow. 1 sweet 1.
Do you have any questions about homework? No? It's okay? Is it hard?
No, in general.
In general, it's fine.
No, not specific the last one. I didn't start.
Yeah, if you're talking about the last one, so we didn't start.
Yeah.
Ah, okay. I mean the third one.
Oh,
4? Ah, yeah. Yes, I started from 0. Yeah.
yeah. So
But the name homework 3.
Yeah, it's okay. I started.
Okay.
the lab showed it in another way, all of these summations.
Yeah. I see. You just treat it as x in some power.
Yes. Exactly.
I mean, you can do this, but
it's the same.
yes, it's the same. You can get the same answer using both.
Also the
Richardson. They did it differently.
Very differently.
How that?
My iPad is shut down.
Ah, okay.
There's no way to know.
Everything is like Laplace and Z transformation.
Laplace and
Z, I don't know. It's
is
just
it
like
in Borel summation there is a Laplace.
yeah.
Yeah.
I did like S was n plus 1 times the S of n plus 1 minus n, no? Like he said, like in the first transformation, he said something like
like this, or
yes.
like this.
Like this. So it's like the same. Like if you say this is like the h, the no. Like
Yeah,
the
I mean,
arrow,
you
the arrow
define-
here is
you
h
can-
minus 1.
Yeah. I mean,
right?
you define step as the difference between
the
two consecutive values, right?
yeah.
But you can define the differences. So if you have, let's say, here is
Okay,
from 0 to 10, you can treat it as how many intervals do you have. So
Yeah.
and
So
n is
it's
number
like
of these intervals.
And then this is like h square, h1.
Yeah. In principle, it's the same. Yeah, but I mean, I use the logic of numerical analysis. He used the different one, but
It's the same.
in the end of the day, it's the same.
Okay.
It's the same Richardson
Same.
as he did. Yeah, don't worry.
Fantastic.
יש לי 4 דקות למחר בנושאים.
מה יש לך?
4 דקות למחר.
4. איך 4 אחי?
פה הסמסטר הזה יהיה.
התחלת?
כן, ביי, טוב.
ביי.
טוב.
אז כאילו קוונטים, יש לי חצי משאלה 4, שאלה 5.
שנשאר לך או שאתה?
כן, שנשאר לי. סטטיסטית לא התחלתי, נומרית לא התחלתי.
זה שתיים אני גם לא התחלתי. זהו, פתח את השאלה הסטטיסטית, ראיתי שעה ראשונה, הייתי כזה, אמרתי הצ'אט שלי לתרגם את השאלה הראשונה כזה כוח לכל זה.
זה לא נראה לי...
ואז הוא בטעות פתר לי אותה. אמרתי לו, לא, כמו שעשיתי.
זה באסה.
הוא כבר עשה, אמרתי מה.
איי.
ונומרת סבבה?
נומרת סבבה.
גם הקודים? טוב,
כן.
הקודים אף פעם אין לי זמן.
לא, הקודים גם סבבה. כאילו, ממש כאלה, אין איזה שהם יחסים.
כן.
חוץ משאלה 4ג' שזה... בקיצור, אני חושבת שכל השיטות האלה, לפתור סכומים אינסופיים, פשוט זה הכל התמרות. הוא אמר שבריצ'רד, נכון הוא אמר שהגמרא אחת של מיכה ושתיים.
כן, היה פה איזה התמרת לפלס.
אז לא, קודם כל זה התמרת לפלס.
מה זה התמרת לפלס?
מה שכתוב על הלוח של 1 פלוס a פחות x פלוס x בריבוע פחות x בשלישית. זה, התמרת לפלס הולכת סכום מ-n שווה...
איפה?
לא, התמרת לפלס, התמרת z, סליחה.
התמרת z?
כן.
מה זה התמרת z?
התמרת לפלס אבל בבדים.
מציע.
יש דבר כזה. טוב, אז שיש דבר.
מה זה התמרת לפלס? אני באמת לא יודע.
זה כמו פוריה רק מ-0 עד אינסוף וגם על הציר הממשי.
כן. אני חושבת שפשוט זה הכל לקחת את זה, להפוך את זה, להעביר את זה מהמימד של...
כן, נכון.
ממשית,
זה כאילו, זה המשכה אנליטית.
כן, או לספירת רימן כמו שהוא הראה בשיעור, או למרחב לפלס, או מרחב פורייני וכו'. תמציא כאילו. זה נראה לי כל השיטות האלה, שזה מגניב, אבל תקראו לילד בשמו.
כן.
אני ממש עייף. זהו, אני שנות סביבה שנות סביבה זה הכי תמיד?
זה בעיה. כאילו ברגע השנת שלך זה רבע שעה,
כל שנת שלו כאילו נשאר באור הוא שנץ. כל שנה שלא נגמרת באור.
הפוך, שנה שנגמרת באור זה שנץ, שנה שלא נגמרת באור.
לא, אבל אני מתחילה באור. שנה שמתחילה בחושך ומסתיימת באור זה שנה. כל שנה שהיא לא שנה היא שנץ.
לא נכון, שנה שמתחילה באור ונגמרת באור זה שנץ, שנה שמתחילה באור ונגמרת בלילה זה נמנום בין ה...
לא בלילה, בחושך.
בחושך.
זה שנץ. גם שנה שמתחילה בחושך ונגמרת בחושך זה שנץ.
זה לא, זה יכול
מה אם
להיות
אתה
שנת לילה ממש גרוע.
מה אם אתה הולך לישון ב5 בבוקר?
לא, זה סתם.
זה עדיין שנץ. אם הלכת לישון באור,
אתה קם באיזה...
אתה כבר לא ישן, אתה שונץ.
כן, אוקיי, כן, זה אני מסכימה. אם אתה הלכת לישון באור וקמת באור זה שנץ, לגמרי. לא משנה כמה שעות.
כן, לא משנה כמה לא ישנת לפני וכמה תשן אחרי.
גם, זה כאילו, אני אתן לך דוגמה, אתה הלכת לישון...
שנץ חייב לבוא.
לא, אוקיי, אני מגדיר אחרת.
לא, עכשיו אתה הולך לישון וישנת כזה 3 שעות בלילה. כי הלכת לישון בבוקר, רגע לפני שהגיע סליחה, וקמת 3 שעות אחר בבוקר. כל זה שנץ, אתה לא אומר כזה שנץ.